Hello and welcome to the course Design Bore Fields with Confidence. In this video we will cover the answers to the different questions throughout the last part 4 of this course, which was all about the hydraulic design of bore fields. And in the first chapter of this part we talked about the concept of the pressure drop, and we said that we have major losses, friction losses on the one hand, and on the other hand we had minor losses you can actually point to in your system. And our first question was actually about these local losses and this local loss factor you use to model that. And what we said is, well, if you want to account for all the local losses in a certain hydraulic path, what you do is you follow the route of your fluid and you simply count everything you encounter. So in this example here, let's start with our green hydraulic path. Let's start at the top line. We go to the left. We encounter one 90-degree elbow, go down another 90-degree elbow, then we pass through a T-junction, but we go forward. We have a U-bend, T-junction back, and then again 2 elbows. So basically these are all the local losses in the hydraulic path that we see here. And what we then do is we take a look at the table, for example like this one, and we say, okay, we have a 90-degree bend. Let's say it's a smooth bend, and let's assume it's almost like a flanged connection. Then we know that each bend is 0.3, and we do the same with the T-junction, where we go right through, and the U-bend. And in the end, we sum everything, and we end up with a local loss factor of 1.8. Now, of course, depending on the manufacturer of your bends, for example, not every manufacturer manufactures in the same way. So perhaps your U-bend is not as smooth, perhaps it's more like a right angle literally. So also your local losses can vary a little bit. So another way of dealing with this is simply take 0.5 as a local loss for everything. To have a little bit of safety margin there. Now over in the textbook at the last question we will see in this video, we actually calculated what the difference is when compared to friction losses, and it's more or less negligible. But what you do again is go through the path, sum all the different losses you encounter, and that you can enter in GHE as the total local loss factor for this lateral or main header connection. In the second chapter, we deepened our insights in the pressure drop and took a look at how this pressure drop is actually used in the hydraulic design of bore fields in particular, and especially in GHE2. Because we discussed in the last part, when we're talking about the design of bore fields using newer state-of-the-art methods, that the viscosity and the Reynolds number is no longer constant in the simulation. It varies with temperature, so it varies over time. And this means that if we're talking about pressure drop, well, we have to define at which temperature and at which flow rate, because also the flow rate is no longer constant in GHE2. And what you can see here is one of the results in GHE2 is actually the pressure drop in function of flow rate for 2 different temperatures, one during extraction when the fluid is cold, and one during injection when the fluid is warm. So given this graph, you can as a designer see, okay, we have this flow rate. If we have it during heating or cooling, during extraction or injection, what exactly is my critical pressure drop? Now, this question is about our intuition, because typically we think, okay, if we have a turbulent flow, our pressure drop will be higher. But what you can see in this graph is that at around 0.5 liters per second, when we are injecting heat into the ground, so when we're cooling, we already transition from laminar to turbulent. But when we're extracting heat, this transition only occurs above 1 liter per second. So let us now assume we are working at 0.55 liters per second. We have a pressure drop during injection when we're turbulent, which is actually lower than the same flow rate during extraction when we're laminar. And this is counterintuitive, because now we have a laminar flow rate which has actually a higher pressure drop than a turbulent one. And to understand that, let us take a look at the friction losses. And this is the equation, the Darcy-Weisbach equation, where we said, well, the pressure drop is equal to the friction factor multiplied by the length of the pipe divided by the diameter multiplied by the density of the fluid and the velocity squared divided by 2. Now, what changes when going from extraction to injection is our temperature, and this has an effect on the density, but ever so slightly. So, in fact, you can say if we have the same flow rate, then we say, well, our pressure drop is proportional to the friction factor multiplied by the length divided by the depth. And since our design is not changing, of course, between extraction and injection, it's proportional to the friction factor itself. And this friction factor, in turn, is a function of the Reynolds number. This Reynolds number, as we discussed, is a function of temperature. Now, to see how it can be that a laminar flow is hence, or has a higher pressure drop than a turbulent one, we have to look again at the Moody diagram. So this is the Moody diagram, and we said, as we discussed in the second chapter of this part, we have our laminar curve, it's 64 divided by the Reynolds number, and imagine our 0.55 liters per second during extraction gives us a Reynolds number around 2000, 1200. So we have a certain friction factor. But when our temperature increases during injection, we actually have a higher Reynolds number, and we're now in a turbulence regime. And this means that we have a different friction factor, and it can in fact be that this friction factor during turbulence is actually lower than when we're working with a laminar flow rate. And because in both cases our flow rate is the same, it's exactly this difference in friction factor that determines that, yes, we can indeed have a pressure drop in a laminar flow rate that's higher than during injection when we're turbulent due to this simple difference in friction factor. And these insights are also what is the explanation of question 2.2. Because here we were not looking at the pressure drop in injection and extraction in function of the flow rate. We just looked here at the pressure drop over time. So if you recall our second chapter, we said, okay, we increase our flow rate, so we're at least transient throughout the whole simulation period, which is what you see here. There are no sudden jumps from 1 hour to the next when we go from transient to laminar and so forth. So this is all at least transient or turbulent. And what we see here is that in summer, we have a lower pressure drop. And this again is because in summer, we're cooling with the geothermal system. Our fluid temperatures are higher. Higher fluid temperatures means better viscosity, higher Reynolds number, and hence we are more to the right in this Moody diagram, meaning our friction factor is again lower. So in summer, we have a lower friction factor, giving us a lower pressure drop. Now the third question of the second part, it was about something else. It was about pump energy consumption. Now we said that, or we introduced in this second chapter also the pump power, both hydraulically and electrically, as well as the pump electricity consumption. And one might ask themselves is, if we have a constant flow rate, why do we care about the temperatures when calculating the pump energy? And to understand that, let's take a look at this energy equation, which was the sum of the pump electrical consumption at every hour of the simulation period divided by the number of years. So basically take an average of the simulation period, given the fact that your pump electrical consumption at every hour is equal to the flow rate through the bore field multiplied by the pressure drop divided by the efficiency to convert the hydraulic power into an electrical power. And if you have a constant flow rate, indeed this Q dot, it does not change. It's not a function of temperature. But as we discussed, this pressure drop is. Because a pressure drop is a function of temperature, because the friction factor depends on the Reynolds number, which depends on the pressure drop. And also your pressure drop is a function of density, which is also a function of temperature, but that has not so much influence, but this friction factor does. So that's why in GHG tool, if you have a constant flow rate, temperatures also play a role when determining the pressure drop on the pump electricity consumption of your system. Now then, moving on to the last chapter of this part, which was all about the hydraulic design in GHG tool itself. And there we discussed the different ways in which your boreholes can be connected horizontally. And we discussed series connection, parallel connection, Tickelman connection, direct connection. And we also said we can combine everything. And what we did here is we have a group of 6 boreholes, hydraulically connected. And you can see that we have basically 2 groups here. And we have 2 groups of 3 boreholes connected in series. And these 2 groups are connected in Tickelman. And the question is, if we have a flow rate of 1 liter per second coming in from the left, what will be the flow rate through each borehole? Now, the way to look at this is to start at the lowest level. So we said, okay, we have here 3 boreholes connected in series, and we know that in series connected boreholes, every borehole has the same flow rate. And because we go in one borehole, out into the next, and so forth. So every borehole has the same flow rate. But this means that basically what we see here, we have 2 groups, 2 times the same flow rate. So our 1 liter per second just has to be divided by 2 groups. So every group has 0.5 liters per second. And since the flow rate through every series connected boreholes is the same, every borehole here is also 0.5 liters per second. Now, of course, this is done all internally in GHETL, but it's just so that you can reason about how the flow rate behaves when you're changing your hydraulic configuration. Now, the next question was exactly about this situation. Because we talked about the difference between plain parallel connections, as you see here on the left, and Tickelman connections. And the difference was that in a Tickelman connection, we make sure that the hydraulic path had the same pressure drop no matter which borehole was selected by the fluid. So the fluid has no preferential borehole to pass through to get a lower pressure drop. In a plain parallel connection, this is the case. So what you see here on the left is that the hydraulic path through the first borehole is actually shorter, and you have a shorter way to the borehole and a shorter way back. So this borehole will have a lower pressure drop and hence more flow rate. Now, why do we say that the figure on the right is then a Tickelman connection and not a parallel connection, although they look very similar when you just follow the red lines? And the reason for that is that no matter the path you select, the length is always the same. And that's because of 2 things. First, we have these 3 boreholes connected in series, so the flow rate through each of them is the same. But also the flow rate is not identical. So we have one combination of U-tubes where the flow goes from left to right, and the other one where it's from right to left. And this means that we can actually combine these groups into one virtual borehole and actually have the situation here on the right. And if you take a look at it, yes, this is of course a Tickelman connection. The length through each group is the same. And since the flow rate is opposite in each string of connected U's, we can also say, yes, this is indeed a Tickelman connection because there is no preferential route. No matter the path the fluid selects, it will be the same pressure drop, the same hydraulic length. The third question in our third chapter was about the pressure drop in this horizontal connection. Now, as said, we have pressure drop in different parts of the system, and we have our vertical probe, which has a certain pressure drop, but we also have our lateral pipes and our main manifold pressure drops, or header pipes. And each of these pipes, each of these different parts of the hydraulic circuit can have a different flow regime because it depends on the flow rates and the diameter, etc. And what you see here in this graph is that we have we have 2 jumps, one at around 2 liters per second, the other one at around 3.5 liters per second. And when we're in extraction mode, we only see one at around 4 liters per second. And the question is why? And this again has to do with the temperature, and the temperature changes the Reynolds number and when we transition from laminar to turbulence. And what you see here is that at 2 liters per second, we transition from laminar to turbulence in the hydraulic pipe, in the lateral connections, when we're injecting heat. And this same transition occurs at 4 liters per second during extraction, because in extraction the viscosity is higher due to the fact that the temperature is lower, meaning that we need a higher flow rate to transition. And in fact, the transition we see in injection at 3.5 liters per second also will occur during extraction, but at a way higher flow rate that's out of range of this figure. And the reason, just for your information, why the jump in pressure drop is higher at 4 liters per second in extraction than it is at 2 liters per second during injection is because when you have a higher flow rate, this last term in your pressure drop equation, the rho velocity squared divided by 2, is also way bigger. So the jump also becomes bigger because the scaling factor where the velocity is included is also significantly bigger, which is why the same increase is not visible in injection and extraction. The last question is again about the local losses. And we said, well, imagine we have a direct connection to the manifold and we switch to a series connection. And then we have to change our local loss factor in our horizontal connection. But the question is, to what? And the way we think about this is, imagine you have a horizontal connection. So we go to a borehole, 90-degree bend, go down, U-bend, 90-degree back. So we have 3 local losses there. If we change that to a series connection, what happens is we go down, U-bend up, and then again down, U-bend up. So we have actually 6 local losses here. And in both situations, we also have the local losses at the manifold. So that's what has to be changed. In the first case, when we have these 3 local losses here and the 2 at the manifold, and we imagine 0.5, let's say as a local loss factor for each of them, we have a total local loss factor of 2.5. In the series connection, we have 3 more. So there it's 4. So it's a significant increase going from 2.5 to 4. But the thing is that this is not very important, let's say in this case, because the most significant change will be we go from a direct connection to a series connection. So our flow rate will be twice as high as in the initial case, meaning that our friction factor and so forth will also be significantly higher. So the fact that our local losses change a little bit is nothing compared to the fact that due to the higher flow rate, everything will have a higher pressure drop. So yes, these local losses are important, but also place it in perspective with all the other changes you are making. And this was everything I wanted to say about these questions in the 4th part. In next part, we will use these insights as well as the insights from the thermal aspects to talk about the differences between single and double U-tube. And we're really going to look at the sensitivities in design and see which solution is actually better from a certain perspective. And it's to teach you that there is no one definitive answer to which geothermal design is best. So I'm looking forward to seeing you in the 5th part of this course.